Now, with network problems, we actually have arcs and nodes. We have already seen arcs and nodes in, arrows and nodes, etc. Call them in transportation, but it's more, commonplace over here. Arcs and nodes are actually your, again, supply and demand points. You can think of like that, but they are showing a network, some sort of, flow. You will see what I'm talking about soon. So nodes are a set of points, also called vertices. Arcs consist of an ordered pair of vertices and represent a possible move between those vertices. So you actually have nodes and arcs going from one of them, from one to the other. There's a flow in there. Okay, you're going from one point to another point. So if there's an arc ij, then movement from I to j is possible. Okay, I is the initial node, j is the terminal node. These are just namings, but definitions not really that important right now, but you can also have a chain from I to j, from k to j, from k to l, etc. And if there's a let's say, well, I to j, k to j, they are going to the same node from two different points, and k to l, there's another vertex coming out from the k. Going another way and not to another node. You will see what I'm talking about soon, but still, a path is actually an ordered path. So from I to j, j to k, and k to l. So all those nodes are connected by arcs and going in an orderly way. Okay, chain is not the same as a path. So for example, 1, 2, 3, this is a chain, but 1, 2, 4, this is a path. Okay, from 1 to 2, 2 to 4. 1, 2, 3, this is a chain because they are connected to each other somehow. But 1, 2, 3 is 1, 2, 4 is a path. So the shortest path. The shortest path is trying to find, has a start point and an end point, trying to find the, as the name suggests, shortest path from one point to another. So how do I go from 1 to 6 in the shortest time possible? So for example, in this question, it would be, I don't know, 1, 2, 5, 6 maybe, or 1, 3, 5, 6. They should be the same amount. 4 to 8, 3 to 8, I guess. We will see in a minute. But still, we are trying to find the shortest path possible from one point to another point. Now, to be able to do that, we will do some calculations. You will see what we're talking about, and try to find the shortest path possible. But there are some constraints, some stuff we need to take care of, and you need to be able to figure out the distance easily. Now, for example, in here, from 1 to 2, well, I have a value of 4 over here. So to get to 2, I will spend a value of 4 at least. So this one has a stopping time, let's call it a 4. I will get to 2 in 4 units, and I will get to 3 in 3 units. Okay, cool. What about to 4? Well, I will get to 4 from 2. I have no other way. So this will be a total of 7 units. Why? Well, I can get to 2 in 4 units of time, and I add 3 to that, so I get to 4 in 7 units of time. What about number 5? Now, I have 2 paths coming in there. 1, 2, 5, 1, 3, 5. So from 2, I can add 2 more, which will give me 4 plus 2 as 6, or I can add 3 plus 2 as 6. Okay, they are the same. So this one has a value of 6. This is actually called an early time. You'll see later on. And from here, I can get to city here in 8 units of time, or from here I can get there in 9 units of time. So the shortest path is 8. I prefer 8 to 9. So I can get from 1 to 2 to 5 to 6, or 1, 3, 5 to 6, a total of 8 units of time. So this is the shortest path I can find, for example. Now, this is the easy stuff. What about a bit different ones? For example, equipment replacements. Now, this is a bit harder, actually much harder. So you can, maybe if you're taking engine economics there, you can see similar stuff over there, but this is a bit different than that one. I have purchased a new car for $12,000. The cost of maintaining a car during a year depends on its age at the beginning of the year, okay, as given in table 1. So I have to pay maintenance depending on the age of the car. So with the high maintenance costs associated with an older car, I may trade in my car and purchase a new car. So I keep purchasing new cars. The price I receive on a trade-in depends on the age of the car. So this is the trade-in price. Depending on the age of the car, I sell the car and get that much money back. to simplify the computations, we assume that anytime it costs $12,000 to purchase a new car, so the price won't change anyways. My goal is to minimize the net cost, purchasing plus maintenance minus money received in trade-ins incurred during the next 5 years. Formulate this problem as a shortest path problem. Okay, now this isn't that easy, but I can do this. For example, we have to define arcs and nodes. Okay, each node will be a year, and each arc will define if I use the same car or not. If I'm using the same car, each year will be connected to each other. Okay, so if I'm using the, for example, same car for years 1 to 4, I will just connect node 1 to node 4. So I will skip node 2 and node 3 because node 1 and node 4 are the starting and ending points of using that car. And at node 4, which is year 4, I will replace the car. And then I will keep going. For the 5th year, I will use a new car. So I will just use the new car from 4 to 5. So I will just, let's say, draw the line from 4 to 5, draw the arrow, the arc from 4 to 5. So if I use a new car every year, I will just, let's say, connect 1 to 2, 2 to 3, 3 to 4, 4 to 5. They will all be connected to each other if I use the same car all the time. So I will just have a connection of nodes and arcs going from year 1 to year 6, because year 5 will connect year 6 and it will end the computations, and I will not buy a new car at 6 right now. So this is just from year 1 to year 6. Year 6 is the end time. There is no cost associated with that, but the cost is coming from year 5 to there anyway. So I have to draw something like this. Now, as you can see over here, from year 1, I can use for 1 year, the same car for 1 year. I can use it for 2 years, 3 years, 4 years, or 5 years. Okay, how can I calculate this? Let's start with the simple stuff. For example, if I use it for just 1 year and replace it. Okay, let's go back. If I use it for 1 year, I'm gonna buy a new car at $12,000 at that year. Okay, and then I will have to pay the maintenance for 1 year during that one, because age of the car is 0. All right, and then I will sell it for 7. Okay, so 12 buying the car, 2 the maintenance cost minus 7 what I'm selling for, and this is 7 the cost. The real cost is 7 for 1 year. Okay, what if I kept it for 2 years? Okay, I bought it for 12. All right, kept it for 2 years, maintenance of 2 plus 4, sold it at the 2nd year, selling it for 6. So 12 plus 2 plus 4 minus 6, cost of 12 for 2 years. 7 for 1 year, 12 for 2 years. Okay, go back. If I kept it for 3 years, so the maintenance is 2 plus 4 plus 5. Trading in for 2,000, I bought it for 12. So 12 plus 2 plus 4 plus 5, the maintenance cost, minus 2, the trading income, 21 for 3 years. What about 4 years? Well, buying for 12, 2, 4, 5, 9, the maintenance cost, selling it for 1. And the cost is 31 for 4 years. What if I kept it for 5 years for all the time? Buying it for 12, maintenance is 2, 4, 5, 9, 12, and selling it for 0 anyway. So this is what I get as a cost, 44 for 5 years. So from 1 to 2, 7, from 2 to 7, 2 to 3, 7, from 3 to 4, 7, 4 to 5, 7, 5 to 6, all 7s, because this is the cost of keeping it for 1 year. For keeping it 2 years, from 1 to 3, 12, 2 to 4, 12, 3 to 5, here, 12, and 4 to 6, 12. Again, cost is 12. For 3 years, 1 to 4, 21, 2 to 5, 21, 3 to 6, 21. For 4 years, 31. So 1 to 5, 31, 2 to 6, 31. And lastly, for 5 years, it's 44, 1 to 6, 44. So let's try to find a solution once again. I can go to 2 in 7 minutes of time, 7 year cost of time, let's say, at a cost of 7, doesn't really matter, it shouldn't have to be time anyways. So for 2, it's the 7, the minimum cost is 7. What about 3? Well, I can get there 7 plus 7, 14, or with one jump in 12. I prefer 12 over here, so I'm gonna write 12. What about 4? Well, I can get there with one jump, 21. Okay, or from 2 to here, so 7 plus 12 is 19, which is good. Or from here, 12 plus 7 is 19, so this is 19 anyways, which is pretty cool for me. What about number 5? So I can go there from 4, 19 plus 7 is 26, or I can go here from 3, which is 12 plus 12 is 24, better, or from 2, 7 plus 21 is 28, no, or directly from 1 with 31, no, 24 is better, so this is 24. What about 0.6? 24 plus 7 is 31, or from here 19 plus 12 is 31, or here 12 plus 21 is 33, no, or here 7 plus 31 is 38, no, or directly with 44, no. So I prefer 31 over here, which means that I can just get a value of 31 if I come from here or here. So the thing is, the best price you can get, the best value for your money you can get if you keep the car for 2 years. So either from 1 to 3, 3 to 5, and 5 to 6, or 1 to 2, 2 to 4, 4 to 6, or 1 to 3, 3 to 4, 4 to 6, I guess, I don't know. Things can change, but still 12, 7, 12, or 31. Either of these options is okay. 2 years, 2 years, 1 year, 1 year, 2 year, 2 year, 2, 1, 2, or 2, 2, 1, doesn't really matter. You can use all those options, but still the best possible thing you can do is keep the car 2 years. You can just find it from here, by the way, by just finding the average yearly cost. For example, average yearly cost over here is 7. Average cost over here is 12 over 2, 6. Average yearly cost is 7, again, 3 years. Average yearly cost is 31 over 4 is equal to 7.75, I guess, close to 8. And 44 over 5 is 8.8. So the best yearly cost is 6 over here. This is something you can do to check what you're doing. By the way, there are other solutions as well. For example, you could go, I don't know, 3 plus 1 plus 1 maybe. No, 2 is best. 2, 2, 1 is best. So yeah, 2, 1, 2, 2, 2, 1, 1, 2, 2. These are the best options you have. But still, this is how you can find the best option in a, more, let's say, yaklaşık, approximate way. Yeah, this is the best yearly value. So this is probably what you're going to use most in your answers. This is not a certainty, but something you are approximating to. But this is a certainty by finding the early times you can get there. So this is actually done with the Dijkstra's algorithm. So there are some algorithms you can use. Mark all nodes unvisited. Okay, everything is unvisited. Assign to every node a tentative distance value. Set it to 0 for our initial node and to infinity for all other nodes. So how many steps I can, or how much time I can, or what kind of cost I use to get there. You can think of it like that. And for the current node, consider all of its unvisited neighbors and calculate their tentative distances to the current node. So what we have done previously is something like this. Compare the newly calculated tentative distance to the current assigned value and assign a smaller one. So we're trying to get there, but you can get there from other stuff, other places. So it's a tentative value. For example, if the current node A is marked with a distance of 6 and the edge connecting it with a neighbor B has a length 8, length 2, then the distance B to B through A will be 8. If B was previously marked with a greater distance than 8, then change it to 8 because 8 is smaller. This is something we have done over here. Okay, we were calculating all the points. For example, 1 to 3, 7 plus 7 is 14. It was assigned 14, but directly from 1 to 3 is 12. So 14 changes to 12. It goes lower. The same thing. So keep doing it until you finish it, as you can see over here. So they are assigning points, then it's trying to assign points to others, and going from there, as you can see, 20 is changed to 12. So trying to find better values, and it's changed to 9 now. 4 plus 5 is 9. So this is a better way, and trying to find values for other stuff as well. So 8 plus 10 is 18, but 4 plus 11 is 15. This is better. So it's done with that one as well. Now it's trying to calculate here. 15 plus 6 is 21. 9 plus 9 is 18. This is better. And we're done. So 18, 0, 4, 9, 18. This is the optimal way. This is what Dijkstra's is doing. This is what we have been doing, actually. Again, another one. As you can see, there are some. It is a bit more complex because the way is a bit more complex. It seems we are trying to go from A to B, so it's trying to find all the values and just calculating them one by one. But still, it's doing the same thing and getting rid of the calculated nodes. When you calculated it and there are no other nodes coming in there, you can just find the value for it, minimum value for it, and you say that, okay, we're going to start from here. Right now, nodes 1, 2, 3, and 6. These are gone from the question. You don't need them anyway, and we're trying to find a solution from there anyways. Or this one, as you can see, you're just trying to find the best shortest path going over here without going over this obstacle. So you started from there, you're just trying to find the easiest way. As you can see, as you get closer over here, you will not be able to find any ways. You cannot go from there anywhere at all. So you have to just find another way, trying to go from there. So as you can see, this path is blocked. I cannot use this path anyway. And it is just showing us how to get there in another way. It's trying to show which is the closest, which is the fastest way, and it's going one by one for each of them. So at any point, yes, it's found the best solution, and it's showing us over here. There might be other solutions as well, maybe alternative solutions, but at this point, this is the shortest solution for that one. Not going over from the top, but going from the right-hand side. So these are just going at the same speed. So any point, for example, if you start from here, this, and this, these 3 points have the same length, 1, and these 5 points have the same length, 2. These 7 have the same length, 3, etc. So at any point, at any time, any point we're gonna find at the edge has the same length with each other. So it's trying to find the best, shortest path over there by going one by one from each neighborhood. So this is how this class works actually. What about other types of problems? Now, this one was the shortest path problem. Now, this is a maximum flow problem. This is different because in a maximum flow problem, you are trying to send the maximum amount of goods from the path. Okay, the path now is a constraint that's limiting your total number of supply you can make from one node to another. It's not a time constraint now. It's not something that you have to, take into consideration for finding a shortest path or finding a minimum cost. This is now a constraint that limits the amount of items you can send. Okay, it's like an, I don't know, for example, a road, and there are cars going over it. Okay, for example, if there are 2 lanes, at most 2 cars can go at the same time, side to side. If there are 3 lanes, 3 cars can go, etc. So number of lanes is your limit as how much cars can pass at the same time. Okay, this is something like this. So maximum flow is just trying to find the maximum amount of flow from one point to another. Okay, so how does this work? For example, Sunk Oil wants to ship the maximum possible amount of oil per hour via pipeline from node SO, which is the source, to node SI, which is the sink. So start point and end point. You can think of it like this in the figure below, as you can see here. On its way from node SO to node SI, oil must pass through some or all of the stations. It doesn't have to pass through all. It can just pass through some. 1, 2, 3. It can pass through all as well. It doesn't really matter. The various arcs represent pipelines of different diameters. So we have pipelines of different, diameters. Their, largeness, let's say, change. Okay, the amount of oil that can pass through them is different. The maximum number of barrels of oil, millions of barrels per hour, that can be pumped through each arc is shown in the table to the right. So these are the capacities, these are their capacities. And let's say each number is called an arc capacity. Yeah. As an example of a possible flow, termed a feasible flow, consider the flow identified by the numbers in parentheses in the figure. So this is a possible flow. Okay, we will check what this is. Formula an LP that can be used to determine the maximum number of barrels of oil per hour that can be sent from SO to SI. So let's take a look. This says that 2, 0, 2, 0, 2, 0. And there's a, from sink to SO, there's a feedback over here. We will talk about it later on. But this says that, okay, I'm sending from source to point 1, 2 units. Okay, and from point 1 to point 2, 2 units as well, and 0 units to point 3, and from point 2 to SI, the sink, 2 units. Okay, this is a possible route. I could also have done it like this. I could have sent 2 units from here and 3 units from here, for example. But if I had sent 3 units from here, I have only 2 units going out of this one. So I cannot send 2 units out of here. I cannot send 3 units out of here. I can only send 2 units out of here. So this extra Y unit would be wasted. It wouldn't be used over here. So I cannot do that. It's not really feasible. 3 units coming from here and going out. That's not possible. But if I had sent 2 units from here and 2 units from here, if I could send that 2 units from 1 to 3 and try to send it to SI, again, that doesn't work because it only has a capacity of 1. So 3 only accepts unit 1 units of capacity. 2 only accepts 2 units of capacity. Okay, so I will have to send 1 unit over here. So this will be only 1. coming back here. This one is going to be 1, and this one is going to be 2. So a total of 3 units can be sent over here. All right, that's the way I can, send it. But I will check what happens later on. So this is a possible, feasible flow as well. This is actually the optimum flow, but still we'll see. How do I model this one? Well, think of this, all these points as constraints actually. All those nodes have flow constraints. They have incoming flows and outgoing flows. So at point 1, or let's go with point 2, this is better. At point 2, you have 2 sources coming in, 2 supplies, and 1 demand going out. So anything that comes from here and here, the total, their sum, should be equal to whatever is leaving point 2. You can think of all these points in balance, okay? They have incomings and they have outgoings. The sum of incomings should be equal to sum of outgoings all the time. So all these arcs will be one variable, one decision variable. So for example, this is from 0 to 1, x01. This is x12. This is x13. This is x3, which one? 4. This is x24. This is x12. This is x02. And this will be over here, the feedback part, will be x040. But this is again something we will, use to balance the model at the last point. We will get there. So all these arcs are variables. So we need to model using those variables. For example, this one, x01 or xso1. xso1 will be at most 2. So xso1 is less than or equal to 2. This is the capacity, and we know that this is a constraint. Capacity is a constraint anyway. So xso1 or x01, however we name it, cannot be greater than 2. So xso1 is going to be less than 2. x13 is going to be less than 4. x12 is going to be less than 3. x24 is going to be less than 2. I'm sure you can understand where I'm going with this one. x3si or x34, whatever we name it, is going to be less than 1, etc. Then all these nodes are one constraints. So there are each of them is a constraint. So for node 2, for example, we have x12 incoming and x02 or SO2 incoming. So x12 plus xSO2 should be equal to x2si or x24, however we name it, x2si. So the sum of these two should be equal to this one, or this one should be equal to sum of these two. So xSO1 is equal to x13 plus x12. And as you can see over here, all the nodes, there are 5 nodes, so all those 5 nodes should be a constant, should be constant. So as you can see, xO, this part is going out from that one. So this is the SO1 plus SO2. So this part is xSO1 plus xSO2 is the leaving constant, okay? The leaving ones. And xSO or x0, it doesn't really matter. This is all the supply you are making, all the supply you are sending out. So all the supply you are sending out should be equal to the supplies going into these pipelines. Same thing for here. All the supply or all the demand coming in should be equal to all the supply you're sending out. So at the end, as you can see, you're using x0 once again. x0 is the supply, which is equal to the demand anyways. So you are trying to find this and balance this one. So this is the hardest constraint that start with these 3, but still, you are sending a number of barrels per hour, whatever, millions of barrels per hour, and this is called XO. And you are trying to maximize this XO. And to maximize this XO, you are trying to find how much you can send from each pipeline. So this one plus this one is the total you have sent from here, which will be equal to total. This one is accepting, this part is accepting, which is equal to the feedback anyways. We don't need the feedback here, but still. This XO is the amount we are sending, which is equal to the first flow constraint from the first node. And after you have sent this from here, this one, SO1, XSO1 is going to be equal to x12 plus x13, as you can see here, which is over here. And it goes on like this. Now, when you find the solution for this optimization problem, you'll find the maximum flow you can use to send, from one point to another. You can send from one point to another. This is just using the, LP and simplex for this one. What about other types of networks? The CPM and PERT. Now, CPM and PERT is a bit more, just a bit more complex from shortest path, but PERT path, shortest path, the PERT path gives us a bit, let's say, a bit more probability into optimization, but just a bit more. Nothing serious, just expected value and variances in there. But still, the CPM is like the Dijkstra's method, but it's a bit more complex because it has early times, late times, etc. You will see what I'm talking about, but still, it's doing the same thing. We have a network model, and we are trying to find how to minimize the time we can, finish a project in. Okay, minimizing the project time. So we're trying to, fit it into a deadline, for example. Okay, there are some constraints, some things allowed and not allowed. For example, in here, there are activities, they're on arcs. So each node is a time, okay? Activity on arc. There are other ways of showing those, but activity on arc is what we're going to use over here. So this is the starting point, for example, and this is the ending point. From 1 to 2, from starting point to a point in time, we are making the activity A. This is an activity in project. You can be recruiting people or using machines to produce something, anything you can come up with, any activity you can come up with, or preparing for the marketing, etc. So this is a project anyway. You can have different activities in that one, and you cannot start activity B before you have completed activity A. And activity A completes on time 2. Whichever time this is, we don't know the exact time yet, but it completes on time 2, and after time 2 is reached, activity B can start. So after activity A has ended, activity B can start. Or something like here, activity A and B is completed. They don't need to be completed at the same time, but they are both completed at a time 3, and C can start from here. Or both B and C are waiting for activity A to be completed. These are all different types of activity and node and arc relations you can see in CPM, but still they all have predecessors. Okay, B is waiting for A, C is waiting for A and B, B and C are both waiting for A. So you have to complete the activity before start the new activity. And so the first node is the start and the last node is the end. So they all start from node 1. They don't really matter. So they all start from node 1. And the finishing node is the ending. So project starts at one node and ends at another node. And an activity should not be represented by more than one arc. So each activity is on one arc, and 2 nodes can be connected at most by one arc. This is the most important part. Probably you cannot have more than 2 arcs going to one node. Okay, from one node to another node. You will see how that's used, but still, the fifth is, for example, over here. Let's say that C is waiting for A and B, and A and B are both starting from the first node, starting node. You cannot send them together to 2. This is not viable. This can't be done. But you can create a dummy arc and a dummy node over here, and you can send B from the starting point to 3 and use a dummy arc, which has a value of 0, time 0. This is a dummy activity, which is a 0 time, and send it to 2. So this is the same thing. The same value is going to be calculated for 2, but this is the right way of showing it instead of this one, because you cannot send 2 arcs to one node from the same node. Okay, you can have 2 arcs coming into the node, but from 2 different nodes. So this is the right way of showing it. Okay, a dummy arc with a dummy arc. So let's start with a simple, example and see how we go from there. We have 1, 2, 3, 4, 5, 6 activities. They are named, they have names, but we don't really care what they are right now. They have predecessors, so they have relationships and duration, days, the time. So how do we start with this one? Well, we start by finding the first activity, which is the starting activity. This activity should not have any predecessors. So we have 2 activities without any predecessors. So A and B are our starting activities. So from the first node, both A and B will leave. Okay, they don't have any predecessors, so they start at the same time with the project start. Then C and D both are looking for A and B. So A and B should be finished at some node, so that from that node, C and D can leave out. Then E is waiting for D, so D is finished at a node and E is leaving from that node. And F is waiting for C and E, so at one node, C and E will have both finished and F will leave. Okay, let's try to, draw this one. Let's start drawing this one. From here, this is the first node, okay, node 1. I know that there will be two nodes leaving from here because both A and B are being waited for C and D. So A and B will end up at the same node at the same time, but they cannot be done. We cannot send it at, with one node. So I'm just going to have to use something like this with a dummy arc. Do I have? No. Let's just use it like this one then. Okay, this one is like this. And then I will say that this is like this, for example. So this one will be A, the activity A, and the bottom one will be activity B. And this is the first one. Let's call this one the second one, dummy one, and this is the third one. So this is the starting node, okay? A is leaving the starting node because it has no predecessors. B is leaving the starting node because it has no predecessors. And they are ending at nodes 2 and 3. And I know that C and D are waiting for A and B. So C and D will start from here because B has been sent over here from 2 to 3 with a dummy arc. So from here, I will have to send out two nodes, at least two nodes. Right now, 2 is not for me. For C, let's send it like that, and D. So when C and D are sent out, they have to end in nodes, of course. There will be two nodes over here. No, this is not going good, but still. So I will have C over here, for example, and D over here. So I'm sending C and D outside. All right. Then I know that this might be something else, but still, E is waiting for D. Okay, there will be something going out from D for E, and F is waiting for C and E. Oh, okay. So at this point, I have sent C over here. If E is connected over here, I can send this F from this point. So I can just say that. Let's draw something like this one. Now, this one is going to be E because E is waiting for D and E is going to be used for F. So from here, I can send out F. So the text will be E over here and F over here. And when F is done, we are done. So this is going to be the ending point. So let's write the node names as well. This is going to be the fourth node, the fifth node, and the sixth node. So this is how I draw the graph, draw the network. Okay. After I have drawn the network, I have to calculate their times. You will get that. But still, let's see if we have done correctly. Next one. Yeah. From the first to the second and the third ones, as you can see, it has written its times as well. It's something we can do. It's easier. And from there, you can just find the values. What values? Early time and late time values. So if you have this graph, you can just find values for every node that shows its early time and late time values. Well, early time it is ET, late time it is LT. They can be calculated using those nodes. It's easy, so I will just show the example. But you can read these, but you will not be able to understand what's going on without just using them hands-on. But when you use them hands-on, you will see that it's actually very easy to calculate. And there's a float thing. The float is the time you have access for some of the activities, which you will understand. And there's a critical path. This is the path that doesn't have any float on it, and it's just the amount of time your project will finish. You will see what I'm talking about on the example. And the free float is the same thing. It's about the early time and late time stuff, but still here. Let's take a look. This here is the, these points are 1, 2, 3, 4, 5, 10, 20, 30, 40, 50, it doesn't really matter. And there are times over here, 3, 4, 1, 3, 3, and 3. Now, how can we find the early time and late time over here? Let's start. Now, we know that the starting point, this is 0. There is no time spent over here. None. And we use 4 points of time, t is equal to 4, to get to 20, and there are no ways of getting to 20, so this should be 4 as well. This is the early time. That's the early time. So this says that you can start at 0 and you can end at 4 for activity B. These are the early times. Okay. For activity A, you can start at 0 and you can end at 3. All right, I can end at 3, no problems there. So what about over here? The time is 1, so I can end at 4. With time 1, spent 1, I can end at 4. And over here, now, to get to the last part, 4 plus 3 is 7. 3 plus 3 is, okay, this is 6. 4 plus 3 is 7. Now, here, I'm going to check the greater value because I cannot finish the project without finishing B and C. And B and C can be finished at the earliest of 7. Earliest time of 7, 4 plus 3. What about here? ADF. Well, 3 here, 1 here is 4. 4 plus 3 is 7. So 3 plus 3 is 6. The earliest time I can finish this one is 7. Okay. Now that I have this one, I will go from here and go back to find the late times. The latest time this node can be finished. Okay, this node can be ready to proceed, let's say. 7 minus 3 is 4. So the value, the latest time this can finish is 4 anyways. 7 minus 3 is 4. Okay, this is 4 as well. 7 minus 3 is 4. Okay, this here is 4 as well. This is different. Now, these were all equal, but this is now 4. Okay, why? Because of this one. But from here, 4 minus 1 is 3. Okay, 3 is less than 4. So this one has become 3 because of this rule. So this is a late time of 3 as well. This has to be here at 3 at most. And this is, of course, 0 because the early and late time is usually the same here. It doesn't have to be, but usually is. Actually, it has to be. So as you can see over here, the early and late times, early time is when you pass forward, and late time is when you pass backwards. And as you can see here, in this table, okay, this one is a critical path because 10, 20, 50, all these activities has to be done on time all the time. ADF is another critical path because these have to be done on time as well, but AE is not. E, this activity, this can start at 3 and then at 6, it doesn't really matter. And it can start at 4 and then end at 7. So this activity has a float of 1. Okay, it can start 1 unit of time later than this node. Now, A has to start on time, B has to start on time, C has to start on time, D has to start on time, and F has to start on time. But E has a float of 1 because it can start at 4 and end at 7 anyways. It cannot start at 5, then it end at 8, and it would land on the project. It's not something we want, but it can start at 3 because the early time is over here is 3. But it also has a float of 1, so it can start at 4 because this 7 is actually 7 over here as well. This 7, there is 3, the difference is 4, and this 4 units can be spent any way we see fit in here or in these lines. But in these arcs, it's 1 and 3 necessarily. You cannot have any float over here, but over here you have a float of 1 because you have 4 units of time to get from point 30 to point 50, but you only use 3 units of time instead of that 4 in activity E. So activity E has a float of 1. This is just really simple to calculate when you start making the calculations by yourself when you get into it. But the PERT parts. Now, with PERT, Project Evaluation and Review Technique, the longer version, you actually have estimates for the activities. Okay, there is a most favorable condition, there is least favorable condition, and the most likely value, like an expected value. Now, you take these 3 estimates, they're actually triangular shape, in a triangular shape. You take these 3 estimates, and you actually calculate the real expected value. This is not an expected value. The M is a most likely value, but it's close to the expected value most of the time, but it's not the expected value. And the variance for these things. Now, this is how you calculate them. A plus 4m plus b over 6, b minus a squared over 36. The expected value and the variance of these activities. And then you just calculate everything like CPM. Let's see. Each hour, an average of 900 cars. Oh, sorry, this is something different. Now, you have those values. You just calculate the early time and late time. For example, the time we have calculated over here, early time and late time we have calculated over here. And you have this critical path. For example, let's just assume that the critical path over here, let's assume that this is our critical path. Okay, there is only change over these two. We don't care about this. This is not a critical path. Somehow this is 2, let's say. So this is not a critical path for us, but this is a critical path. So we know the values for B and C. Okay, the amounts of time we have for B and C, the expected values, and the variances. Okay. So, for example, we have an expected value of total of for B and C 7 and a variance of total of 36, for example. Okay, 7 and 36, let's call them. And it's asking us what's the probability that the project ends in time of 9 units of time. So we know that the average is 7, the variance is 36, so the standard deviation is 6. And it's asking us the time we spent, the probability of time we are spending is 8 or 9 or 10, whatever. What are we going to do? Well, we just use the normal approximation method, something we already know. We'll just use the, I don't know if you remember the version of it, but that was Z, let's just Z minus mu over, let's call it sigma. Do you remember this one? I hope you do. I really hope you do. Z minus mu over sigma. So you'll just use this to, approximate normal, use the normal approximation. And from there, we'll calculate the probability. That's it. This is what PERT is all about, actually. We are trying to find the expected value and the variance, the total expected value and the variance of the project. And then it's asking us a question about the total project time, and we are trying to find the probability of the project time being, at least that much or at most that much, whatever it's asking us. But all we need to do is just calculate the total expected value and variance on the critical path. And then we'll just use that for Z minus mu over sigma for the, calculation. And then use the Z table. That's it. And the last network type is the minimum cost network flow problems. So cost and flow are together here. Now, in this one, there are, this is actually best represented on the traffic issue. An average of 900 cars enter the network in the figure below at node 1. Okay, 300 of the cars seek to travel to node 4. We're trying to go over there. So there is a demand here, a supply here, a demand here. The demand and supply are not just on one point. They can be on more than one point. Okay, 500 cars will travel to node 6. All right, and 100 cars will travel to node 5. Okay. The time it takes a car to traverse each arc is shown in the table. In the figure, number above each arc is the maximum number of cars that can pass by any point on the arc during a 1 hour period. So in here, we have a capacity constraint, a time constraint, and a demand and a supply. Lots of things over here. It's a jungle. So we will have to try to find the best, minimum cost and maximum flow thing here. So we're trying to minimize the total time. Okay, we are trying to minimize total time, but we have flow constraints as well. From 1 to 6, for all cars to travel from node 1 to 6. Okay. So over here, we know that we have some supplies and some demands and some capacities as well. Okay. What we need to do is just find how we can, get the best time, the least time available. Okay. So we know the times over here, given times over here. So from 1 to 2, it's 10 minutes. From 1 to 3, it's 50 minutes. From 2 to 5, it's 70 minutes, etc. And we also have over here capacities and nodes for them. So for example, we already know from the maximum flow problems, for each node, we have incoming cars and leaving cars, which is cool. So for example, for node 1, all right, we know that from 1 to 2, there are some cars going. From 1 to 3, there are other cars going. And from 1 to 2, and 1, 2, 3, x1, 2, and x1, 3, their total should be equal to 900 because 1 is a supply point and it supplies 900 cars per hour. Okay, so 900 is going to be equal to x12 plus x13. Okay, what about point 2? Well, x12 is my supply to point 2. From 2, I will have two demands, x24 and x25. So x12 is equal to x24 plus x25. Okay, what about point 4? Now, with point 4, we have a demand point as well, just like a transshipment problem. This point is a supply point and a demand point, and there are two supplies coming into it. One demand going out here, one demand going out here, and one internal demand, let's call it, because 4 is a sink point. Okay, there are 300 cars that's going to be going out of the network at point 4 because 300 cars are trying to get to point 4. So whatever number of cars I send here, 300 of them will disappear at this point, and the rest will go out. So x24 plus x34 will be equal to 300 plus x46 plus x45. Same for point 5. There are 100 cars going to point 5. So x25 plus x35 plus x45 is going to be equal to 100 plus x56. And with point 6, which is just a sink point, there are no points going out, it's just a demand point, x46 plus x56 is going to be equal to 500, I guess. Yes. So when I just model this with capacity constraints, x12 is less than 800, x13 is less than 600, etc., and use those times to find the minimum time. So 10 times x12 plus 50 times x13 plus 70 times x25 plus 30 times x45 will be minimized. I get the solution I'm looking for, which is this enclosed form. So this is the minimization of time. These are all the nodes, node constraints, incoming supplies, outgoing demands, and this is the capacity constraint for each arc. So minimize the cost of arcs, make sure the arcs are in constraints less than their capacity, and these are for the nodes. All nodes are in balance, supply of nodes and demand of nodes. So this is how we can solve the MCNF problems, minimum cost network flow problems. Okay, any questions?